Alright, I am Noah Little, and although I am not as talented as my physics teacher, I will try my best at teaching you light reflection. So, if you'll please just get out your notebook and follow along, make sure you understand the lesson objectives and the vocabulary. As you listen, please keep detailed notes. You will have a few, I'll have a few demonstrations for you, and that would be a great time to pause the video and record it in your notebook. They are great to reflect upon and to use in future tests until you have them completely incorporated in your mind. Have you ever wondered why light reflects differently from different surfaces? Consider what happens when a light wave represented by a simple ray of light strikes a flat surface of glass or water. To understand what happens, first consider a smooth surface of a transparent medium such as water and consider light striking it from a particular direction. Because the water is transparent, part of the light passes through into the lake, but part of the light is reflected. The light reflected from the lake forms a spectacular image, but when the water surface becomes rough from ripples and waves, the reflections are much less distinct. The law of reflection relates angles of incidence and reflection. To describe the way light reflects from a surface, draw a typical ray of light, keeping in mind that the ray is an imaginary line describing the path and direction of the light wave. At the point where the ray strikes the glass, draw a perpendicular or normal to the surface. The angle theta I between the normal and the incident direction is the angle of incidence. It is always measured from the normal, not from the surface itself. The angle theta R between the reflected ray and the normal is the angle of reflection and lies in the same plane as the normal and incident ray. The law of reflection states that the angle of incidence is always equal to the angle of reflection. That is, theta subscript R equals theta subscript I, or the reflection equals the angle of incidence. So here is the example. Hopefully you can see it. You have your angle of incidence is equal to your angle of reflection. Here's your normal line, and you measure it from the normal line. And so, why would light obey the law of reflection? The law of reflection can be explained in terms of the Huygens principle, and the wave character of light is the wave fronts arrive at the surface. Each point on the surface acts as a source of a new wave. The new wave has the same frequency and the same wavelength as the light reaching the point, and is in the same part of its oscillatory motion. As each point on the wave front reaches the surface, it reflects to send out part of a wave, and the new wave fronts are of the same distance apart. Again, going back to our example. Why do you see clear images in the surface if the surface is microscopically flat? To see an object, light waves from the object must reach your eyes. If a surface is smooth and flat like the surface of a still life or a mirror, the law of reflection applies. The incident rays at a particular angles with respect to each other keep the same angles, and the waves of light coming from a point on any object come to your eyes after reflection, as if they had come directly from where you see the reflected image. You see the reflected image as if it were behind the reflected surface. This kind of reflection is called specular reflection. Definition of specular reflection is reflection in which the rays travel in a definite direction, in which the angle of incidence and the angle of reflection are equal with respect to the normal. Specular reflection is a flat surface changes the direction of all the rays of light from an object in an organized way, so that the eye sees them as coming from the location of the image in the mirror. This is why when you're standing outside of one of the big pretty buildings, say a mall or a superstore, and you stare into the windows trying to see what's inside, but you're seeing reflections of, say, the trees outside, it looks like there's trees inside. This is because the way that the light is bouncing off in the specular reflection makes it appear as if the image is beyond the glass, even though it's being reflected. The law of reflection applies to rough surfaces. The surface of paper, when looked at microscopically, is rough and irregular. Parallel light rays striking this rough surface or a similar one create great variation in the orientation of the normal vector, which results in reflected light rays being sent in almost random directions. The law of reflection still applies. Each ray of light representing the direction of waves has an angle of reflection equal to the angle of incidence, but because of the roughness, the orientation of the surface varies for each ray of light. The angles of incidence and reflection are very different from those of nearby rays striking the surface. The result is that light striking the surface is scattered into many different directions. The kind of reflection that results is diffuse reflection. Definition of diffuse reflection is reflection in which the rays travel in all directions because of microscopic irregularities in the surface of a medium. So then we can get into another one of our examples. So you see, I have to make sure that I can see it. If I can't see it, you can't see it. So, here is your typical reflection. It comes in smooth and it bounces off in the same angle. But in your diffuse rays, it comes in and it bounces off a crazy direction. It comes in and it bounces off a crazy direction. It comes in and it bounces off a crazy direction. That's because the light is diffusing and going in different. It's still following the law of reflection, but because it is not smooth, it is being reflected in multiple different directions. It's diffuse. Some of the light striking a transparent surface is also transmitted. Consider what happens when light crosses a surface to enter a transparent material such as glass or water. The light waves striking the surface result in both reflected waves and waves entering the new medium. Light that enters the new medium can change direction, a phenomenon known as refraction. Definition of refraction. Definition of refraction: the change in direction of light when it goes from one medium into a different medium. The angle of refraction is the angle of the refracted wave relative to the normal. Refraction occurs because light travels more slowly in a transparent substance than in a vacuum. The index of refraction, N, describes how slowly the light travels relative to the speed in a vacuum. Water has an index of refraction, N equals 1.33, meaning that the speed of light in water is C divided by N, or C divided by 1.33, where C is the speed of light in the vacuum. Very simple. Where speed is the speed of light in the vacuum divided by the speed of light in water. Let's see if we have a example of this one. It just so happens that we do. As you can see, we have our normal line straight up and down here. We have our light wave coming in at a 45-degree angle, and because of refraction, it's going to go into a 32-degree angle relative to the normal as it goes into water. That is because it travels more slowly in water than in air, or a vacuum. The change in speed explains the bending. When you look at these diagrams, you can see that the light appears to be bending as it enters a glass surface or a water surface. As each wave front strikes the surface, each point on the surface not only radiates a reflective wave but also a wave that enters the medium. The frequency is how many times per second the wave oscillates, so it cannot change as it crosses the boundary. But the slower speed of travel in the medium means the wave fronts are closer together. For this wave fronts to match up with the wave fronts that are striking the surface and producing the relative wave, the wave's direction must change as shown in our diagram. Because the change in speed is different in different substances, the angle of refraction for a given angle of incidence depends on the substance. It varies. There's no constant. It varies. Do you ever try to see what's happening inside of, say, a pool or a lake when you're swimming or you're fishing? If you look at a glancing angle along the surface from underwater, sometimes you can see nothing except reflections of what's under the surface. Why do you think this happens? The reason that you're unable to see objects outside the water has to do with the angle that the light is traveling relative to the surface of the water. The light ray is traveling along the top surface of the water. What happens when light shines from a medium with a higher refractive index to a medium with lower refractive index? Let's learn more about why you sometimes see only reflected images underwater. Think of light shining from a medium of higher refractive index such as water, where the light travels more slowly into a medium of slower refractive index such as air. If you shine the light straight up, some of it leaves the water while some of it is reflected downward. If you shine it at a larger angle to the normal, some light that leaves is at even greater angle to the normal. At some angle of incidence, however, the reflected light travels right along the surface. This angle of incidence is called the critical angle. Definition of critical angle: the angle at which the reflected rays lines along the boundary of the two media. At the critical angle, the refracted light is at tangent to the surface at 90 degrees to the normal, and it travels right along the surface. At the angles equal to or greater than the critical angle, you cannot see outside of the water. Very simple. So, the critical angle is determined by the indices of the refraction of the two materials. Because the speed of light is c divided by the index of refraction n, an index of refraction of 1 would mean light travels at a speed c through the medium. The refractive index of air is also close to 1. When light passes from one medium to another, the ratio of indices of refraction determines the critical angle according to the following equation. This one I drew. You have sine times theta critical, that would be your critical angle, is equivalent to or equal to n2 divided by n1. Again, very simple. This can be used to calculate the critical angle, but remember that there is such an angle only for light that goes from a higher index n1 to a material with a lower index n2. Higher to lower, not lower to higher. Simple. Total internal reflection has many uses. For light leaving a material at any angle greater than the critical angle is total internal reflection. Can we get a definition on that? The phenomenon in which all light is reflected back into the internal medium from which it originated. All the light is reflected with hardly any loss of intensity. The critical angle depends on the index of reflection and is therefore different for different materials. Understanding total internal reflection has become very valuable knowledge because the loss of intensity in reflection is very small in fiber optic cables. Total internal reflection keeps light confined and traveling along the length of the fiber. Total internal reflection also is put to use in optical instruments such as single lens reflex cameras, and total internal reflection is the phenomenon that amounts for the brilliant reflections that give a diamond its sparkle. At an angle of incidence greater than the critical angle, the light wave cannot travel into air but results in total internal reflection. A prism is used in a single lens reflex camera to change the direction of the light path, resulting in total internal reflection. So, to sum it all up, you have light with its properties including refraction, which is explained by index of refraction. You have reflection explained by the Huygens principle in its types of diffusion, specular, and internal. Light striking a surface exhibits both reflection and transmission. Recap. Reflection is the redirection of light from a surface back into the original medium. The angles of incidence and the reflection are always measured from the normal or perpendicular to the surface. The law of reflection states that the angles of incidence and the reflection are equal. Specular reflection occurs from smooth surfaces and results in parallel incident rays remaining parallel upon reflection. Diffuse reflection occurs from rough surfaces and results in scattering parallel incident rays in numerous directions. Light entering a new medium can change direction due to the change in speed of light in the medium, and light from within the medium is subject to total internal reflection if it leaves at an angle of incidence greater than the critical angle. Again, I thank you for watching this video on reflection. I'm hoping that I shed some light on reflection for you. This would be a great time for you to read the recap online. Make sure you understand your vocabulary. Proceed to the test. Please make at least an 80 or above to pass. If not, please feel free to review the material, lessons, the vocabulary, the notes, and the previous lessons to make sure that you fully understand light and its principles. Again, thank you. This was Noah Little doing his physics video project. There we go. That'll work. Goodbye.